Okay, now we're back and we're going to find the second eigenvector, which is through a process which is very similar to finding the first one. So we evaluate the matrix, the coefficient matrix C, at the second eigenvalue, doing this, and we can see what it is here. And we have to find the solution of the linear equations whose augmented matrix is this and whose right-hand side vector is 0. So we start off by doing row reduction, and we can see that we want to get a 0 here and a 0 here. So if we add or subtract 3 times the first row from 4 times the second, that'll get a 0 here, and then the first row from 4 times the third row. So we do that here, and we can see that the second row is now the negative of the first row. So that's good. So we can complete the row reduction by adding the second row to the third row using this, and we can see that we've got a line of zeros in the second row, in the third row rather, indicating we've found a non-trivial solution. So we can choose the third element to be anything we like, so let's choose that to be 1, and then that tells us that the second element is 5/11ths, so we put that in here, and then the first element is 5/11ths plus 1 times the divided by -4. So we do that and multiply the whole thing by 11 to get rid of all the fractions, and check that we have indeed found an eigenvector by multiplying it by the matrix, and we can see that the result is indeed 0. Well, we now go on to the third eigenvector, and I'll run through this very quickly because it's the same as the previous one. So we evaluate the coefficient matrix at the third eigenvector, and we can see what that matrix looks like, and we can apply row reduction to solve the set of equations. So we add 3 times the first row to the second, and the first row to the third. So there it is there. So we execute that, and we can see now that the second row is the negative of the third row. So we can finish the process by adding the third row, or the new third row is the old third row plus the second row. So we do that, and that gives us that, and we can see again that we've found a non-trivial solution because the bottom row is all zeros, and therefore the matrix is singular. So now we choose the first element to be 1, and that tells us that the second element will be 5/4, and then the third element will be 5/4 plus 1, and then we can multiply the whole lot by 4 to get rid of the fractions, and that's the third eigenvector, and we can check that using this. So now we've found the 3 eigenvectors. So what's the general solution? Well, the general solution will be some constant times the first eigenvector times the exponential of t times the first eigenvalue, and likewise plus b times the second eigenvector times the exponential of t times the second eigenvalue and c times and so on. So we execute that. And there's the general solution to the problem. So if we had any particular problem, we would now have to find equations for the constants a, b, and c from the initial condition. So let's establish those as a vector. And as I say, found from the initial condition. So let's just do one of these quickly just to see what it looks like. So we take some initial conditions that x, y, and z at t equals 0 are all 1. So we establish a set of linear equations by subtracting the initial or the general solution we get that, and that's because we forgot to do this one. So we subtract off the x, y, and z and evaluate them at t equals 0 and apply the initial conditions, and we can see that we get 3 equations for the 3 unknowns. So we again turn the Gaussian elimination handle and define the coefficient matrix using this, and then the augmented matrix can be found by joining this matrix, or each row of the coefficient matrix, to the corresponding or the negative of the corresponding number here. And we can do that, and that gives us the augmented matrix, and we can look at that as a matrix using this. Anyway, what we want to do now is find the coefficients a, b, and c by row reduction, and the first thing we do is to swap the first and the third rows, which we can do using this, and visualize it using this. And now we want to continue the row reduction, so we want to get a 0 here, and we see we can do that by adding the first row to the second, and now we've got and we can see what that looks like using this, and indeed it has succeeded. And now we want to finish this, so we want to get a 0 here, and we can see that we can obtain that by adding the second row to 4 times the third row. Sorry, 4 times the second row to 16 times the third row. We could have done it the other way. Anyway, this is the simplest way, and we get this matrix, and so this set of equations is in row echelon form, and we take the we multiply this matrix by the variables a, b, c, and -1, and take the scalar product with the augmented matrix, and that will give us a set of equations which looks like this. And we can see that the third equation only involves c, so we can solve that. We can set the third equation equal to 0 and solve for c to find its 2/15, and then if we look at the second equation, we can see it only contains b and c, so we can substitute for c and we'll get an equation for b. which we can solve. Well, the equation is the second equation, where we insert the solution for C and we solve the result for B. And that gives B. And finally, we conceive that the first equation involves all three variables, but we've found B and C, so we can back substitute them into that equation and set the result equal to 0 and solve for A, to find A is minus a 12. So now we've found the solution for this particular problem, and it'd be nice to see what it looks like. So we can do that by taking the solution, which is a vector of functions, and inserting the solution for the coefficients and plotting the result or the parametric function using this. So we do that, and there's the result. So you can see it's not a very interesting looking function, it's almost kind of linear. Anyway, that's the solution to all those kind of problems. So I want to stop the recording now.